I welcome you all to this video lecture. Here I am going to demonstrate the 6-step voltage source inverter. Basically, we are all having some basic knowledge about an inverter. An inverter is a switching circuit which converts the DC input into the AC output. For this inverter, the design may be with respect to the lot of switches like SCR and the IGBT, the MOSFET. This particular 6-step voltage source inverter is going to design with MOSFET as a switching device. This MOSFET is also a fastest switching device, and it is having their own turn on and turn off control. While comparing this MOSFET with the SCR, the SCR can be turned on with the help of gate pulse. It cannot be turned off with the gate pulse. Whenever it is receiving the forward bias, it will conduct. Once turned on, it will conduct up to it is receiving forward bias. If it is fed with reverse bias, means at the time only it will switch it off, which means the SCR is a semi-controlled switch. We can only turn on the SCR. We cannot turn off the SCR with the gate pulse. While seeing the MOSFET, we can turn on and turn off with the help of gate pulse. For this inverter operation, the switching is very indeed one. The fast switching is very important here. The performance of the inverter is fully depends upon the switching frequency and the switching turn on and turn off control of the switching device that you are going to use. So these MOSFETs, the characteristics of MOSFET is feasible to make this 6-step voltage source inverter. So let me see the power circuit diagram for this inverter. This diagram represents the circuit for making the 6-step voltage source inverter. The VDC represents the DC input source, and S1 represents switch 1. Actually, it is a MOSFET. So S1 to S6, totally 6 MOSFETs are used here for producing 3-phase square waveform as an output. So S1, S3, S5 and S4, S6, S2. These are all the total MOSFETs. These S1, S3, S5 are upper MOSFETs, and S2, S4, S6, these are all the lower MOSFETs. The table represents a firing angle. Before going to analyze the term firing angle, we have to be very clear with this firing angle. What is firing angle? Firing angle is an electrical angle at which the gate pulses are arrived and to make the MOSFET to conduct. MOSFET that is switched on whenever the gate pulses are received. Okay, so the angle at which the gate pulses are arrived, it is called as firing angle. So in this inverter application, we are not switch on the 6 switches simultaneously. We are making the switched on time period at each and every time. So this table represents the firing angle for 6 switches. So S1, the switches is S1 represents the MOSFET 1. This switch is switched on at 0th degree. S2 is switched on at 60th degree. S3 is next 60th degree, which means 120th degree. S4 is 180th degree. S5 is 240th degree, and S6 is 300th degree. So please verify the firing angle in this gate pulse diagram. So gate pulse 1, which means the gate pulse that is devoted to the MOSFET 1. Okay, it is having firing angle 0 degree, which means the MOSFET is fed with the gate pulse from 0 degree itself. So 0 degree itself, the MOSFET will start conduct. So S2, that means gate pulse 2 is arrived at 68th degree. Refer this table here. So S3 is having 120th degree, 180, 240, and S6 is 300th degree. So you may get an idea while seeing this table, which means each switches are switched on with a phase interval of 60 degree. Okay, 0 to 60, 60 to 120, 120 to 180, likewise. So each switches are switched on with 60 degree phase difference. And the another thing we have to note here is the upper MOSFETs and the lower MOSFETs are having the phase differences of 180 degree. S1 and S4 are the first upper lower MOSFET set. So S1, S4. S1 is switched on at 0 degree, S4 is switched on at 180 degree. So phase difference is 180 here. So S3 and S6, 180 degree phase difference. So likewise. And another thing we have to note here is the adjacent MOSFETs are having 120 degree phase difference. S1, S3, 0 degree, 123 degree. So the phase difference is 120. So S3 and S5, S3 and S5, 120 degree, 240 degree. So the phase difference between the switching on the MOSFETs is 68 degree. And let me see the pulse diagram, gate pulse diagram here. According to the pulse width of the gate pulse, the operating mode is divided into two. That means first one is 180 degree conduction mode, the second one is 120 degree conduction mode. First we will see about 180 degree conduction mode. In this mode, the MOSFET is going to conduct for 180 degree electrical phases. So another 180 degree the MOSFET will not conduct. There is a reason to say MOSFET is conducting. There is another reason to say MOSFET is not conducting. Okay. The reason for MOSFET conduction is the arrival of gate pulse. The reason for the MOSFET that is not conducting is the absence of gate pulse. So this conduction will fully depends upon the gate pulse. So we can say this concept with the help of gate pulses also. So let's see the pulse diagram for the MOSFET 1. The pulse in this particular conduction mode, the gate pulse 1 is arrived at 0 degree and it's continued up to 180th degree, because which means 0 to 180 degree the gate pulse 1 is having its turn on time. The rest of the cycle will said to be turn off time, or otherwise the absence of gate pulse. Likewise, each gate pulses are having 180 degree turn on time and another 180 degree of turn off time. You are giving the gate pulse for 180 degree, the MOSFET will conduct for 180 degree. Then this mode is called as 180 degree conduction. So likewise 120 degree conduction. 120 degree conduction mode, it is similar to the 180 degree conduction mode, which means the MOSFET will conduct only for the 120 degree electrical phases. The rest of the cycle, that means 240 degree electrical phases, the MOSFET will not conduct, because the gate pulses is, note it out, the gate pulses is given only for 120 degree. Check the 120 degree turn on time for each and every pulses. The rest of the cycle 240 degree, the gate pulses are having its turn off time. Okay. The difference between the two conduction modes is only the pulse width. We can specify the operating mode with the help of pulse width also. In 180 degree conduction mode itself, the pulse width of the gate pulse is 50%. Is it not? Please check out here. 0 to 180 is turned on. 180 to 360, exactly the 50% pulse width here. So 50% will turn on, 50% will be turned off. Here 120 degree conduction mode, the pulse width will be 33.33%. The other will be the turn off time. Okay, it is the basic difference between these two conduction mode. The another difference, the main difference will be the output waveforms. The phase and line voltages will be exchanged, will be get changed for these two conduction mode, and the switch while seeing about the switch on switching circuits here, whenever you seeing the 180 degree conduction mode, at each and every electrical phase at 0 degree means 3 switches is simultaneously switching on. Means check out here, at 0 degree the gate pulse 1 and gate pulse 5 and gate pulse 6 is presented, which means S1, S5, S6 is switched on. These three MOSFETs are in active mode. Okay, so likewise check out here 68th degree, gate pulse 1, gate pulse 2, which means MOSFET 1, MOSFET 2 and same MOSFET 6. So 180 degree conduction mode, at a single phase 3 switches are switched on, but while seeing about the 120 degree conduction mode, at a single phase only 2 switches are turned on. Check out here 68th degree, the MOSFET 1 and MOSFET 6 is switched on. So this is the basic difference between these two conduction modes. Let me see the output waveforms. Basically the circuits are simulated with the help of MOSFET. The waveform represents the phase voltage that are measured from the 180 degree conduction mode. Here the VAN represents the voltage between A phase to neutral, and the VBN and VCN here. These three waveforms are representing the phase voltage, and take a complete waveform. It is a complete waveform, so it is square waveform here. So one complete waveform is having 6 steps. Check out here. Step number 1, step number 1, step number 2, step number 3, step number 4, 5, 6. Because we are going to switch the 6 switches. Switch on the 6 switches sequentially. So the 6th step will produced at phase voltage, at the phase voltage. Okay, so for this reason only the inverter is called as 6-step inverter. Okay, so these waveforms are having peak values, 2 peak values, peak 1 value and peak 2 value, and the peak 1 value is nothing but 2/3 of V input. If you are giving V input, that means DC input as 24 voltage, means the peak 1 value will be, it is peak 1 value, the peak 1 value will be 2/3 of 24, that means 16 volt. Likewise the peak 2 value is in the range of 1/3 of V input. Let's consider the same 24 voltage. If you are giving the 24 voltage input to the inverter, means the second peak will be, the peak 2 will be 1/3 of 24, that means 8 volt. So it represents the lower, that means the negative region. In the negative region, peak minus peak 2, that means minus 8 volt, minus 16 volt. These voltage levels are constants for each and every phases. The next one is line voltage. Line voltage, we know that the voltage that you are measuring from one line to another line, which means one phase to another phase, VAB, VBC, VCA, like that. This line voltage is having 3 level of outputs, that means 3 level of voltage outputs. That means first one is maximum output, 0 minimum output. Maximum is equal to the V input. If you are giving the 24 voltage to the inverter, means the maximum line voltage will be plus 24, 0 minimum will be minus 24. It is a simple line voltage waveform for the 6-step voltage source inverter. These two phase and line voltages are predicted from the 180 degree conduction mode. Next, the phase voltage represented, the phase voltages that we are obtained from the 120-degree conduction. The only the main and basic difference between these 180-degree and 120-degree is interchanging their waveforms. The line voltage is here the phase voltage. In 180-degree conduction mode, the line voltage is similar to the phase voltage of 120-degree conduction. The phase voltages of the 180-degree conduction mode is similar to the line voltage of the 120-degree conduction mode. So likewise, the phase voltage in 120-degree conduction mode, the phase voltage is having three levels of output. First one is V max equal to V in 0, V minimum equal to minus V in. Okay. So next one is line voltage, as I told that. So the line voltage is similar to the phase voltage of 180-degree conduction mode. Okay. So this complete waveform is having 6 steps. Okay. So basically, this inverter is producing the 6 steps for its phase voltage as well as the line voltage. Whatever may be the conduction, it will produce the line voltage and phase voltage in terms of 6 steps. Then only this inverter is called as 6-step voltage source inverter. We are feeding the circuit with the help of DC voltage. Then only it is called as 6-step voltage source inverter. If you are feeding the inverter circuit with the current source, means the circuit is called as current source inverter. Here I demonstrate the working operation of voltage source inverter, and the second and third part of the video will contain the simulation results of this inverter using MATLAB as well as PSIM respectively. Please post your comments and queries. Thank you for watching this video. Thank you very much.